Alright, this is problem 96 of Neetcode 150, swim in rising water. This is a hard problem. So we're given a squared 2D matrix of distinct integer grid, where basically at each position we have the elevation of the water at this position. Okay, so we're being told that it starts to rain at time 0 and that the water can rise. Alright, we know that at time t, the water level across the grid is t's, okay. So it basically increments monotonically by probably 1. We're being told that we can swim horizontally or vertically, so we cannot swim diagonally. And we can swim in a grid between two adjacent squares, so we can't find a wormhole and actually start from the beginning and go directly to the end. Okay, that makes sense. We're starting from the top left, and we have to return the minimum amount of time that will take us to reach the bottom right. All right, so we start here at 0 and we want to go at 3. What is the minimum time? So, well, basically, after time 1, everywhere, well, the water is going to be incremented by 1, right? Everywhere except at this 3. So this is going to be, it's going to be 1. Because one thing we have to consider is that if the value, for example, at time 1, the value is gonna increase by 1, but for example, the 3 is not gonna increase, so we won't have like a 1, a 2, a 3, and a 4, because otherwise we will never reach the bottom, because we can only swim from a case to another one if they are of the same value. So by incrementing them by 1, well, we are gonna have a 1 here. We're gonna have a 2 here, and basically this is the final case is not going to increment, because otherwise, right, we're never going to change it. So it will actually takes 3 time before this case at the top left has a value 3 and allow us to actually go up to this this level 3, right? Okay, so if I take a look at this example, we can see that we have a clear path here that goes from the top left to the bottom right, and it has the smallest well, the smallest biggest value here is, which is 8. We can see that we could choose another path. For example, if we just go along the left side to the bottom, and then from that bottom left to the bottom right, the greatest value here in this case is actually 12. So it will take us a time 12 to reach the bottom right. But in the current path that we're taking, the greatest value is 8. So at time 8, all these cases will be of the same length, and we will have a straight path to the bottom right starting from the top left. All right, so basically what we're going to have to do is that we're going to have to create we're going to call we're going to use breadth first search, and we're going to go see all the neighbors. And for all the neighbors, we're just going to use, we're going to store them in a min heap, and we're going to, on the next round, pick the top value of that min heap, so that we just go towards the value that takes the less time, so the smallest case. So you can see here that starting from 0, we would have had 9, 14, and 1 on the min heap. So the next value we'll have picked is basically the smallest one, so it's 1. And starting at 1, we're going to have 9, 14, 4, and 2. Notice that we're not going to include 0 because we actually saw it before. And if we actually don't keep track of the value we saw, well, we would have come back to 0. And then from 0, we will have come back to 1. Infinite loop. No time to lose on this. So let's just mark this as seen. And then we're going to go see 2. From 2, we can go see 4. And basically what we're going to have to do is that we're going to have to keep track of the greatest value we've seen so far. So we're going to have to create somehow a value that stores 1 at this place. Now that stores 2. When we go here, we're going to go store 4. Now we're going to go store 8. At 7, well, we're going to still have 8. And at 6, we're still going to have 8. And this is the value we're going to return, 8. So let's go ahead and solve this in a very efficient way. So first, I will keep track of n, which is going to be the length of the grid. And notice that we have a perfect square. So the length of the rows and the length of the columns are actually the same. We want to keep track of a set that will keep all the values we've seen so far. So let's call this scene. I also want to create a min heap. And what do we want to store inside our min heap? Well, definitely the current row and the current column we are at, and also the level of the water we are at. So what I will do is that I will first store the grid at the top left case. So it's going to be at the row 0 and at the column 0. So this is the first thing I am storing in. And that's an error. Okay, perfect. So now that I have this, I can actually add in scene my well, I will add a tuple representing the coordinates of the case we've already seen. And now we are going to use a while loop, and we want to while until the min heap is empty. Because if the min heap is empty, it means that on the previous round we didn't add any values, meaning that we probably reached the end, or we have just no value to return, because there's, I don't know, there's a rock blocking the way from the top left to the bottom right, so we can't traverse this graph. That will not happen though, but still we're gonna use this while loop until basically there is a min heap. And now the first thing I want to do inside this call is I want to retrieve my level, right? This is the first thing I stored. So what is the level of the first value we're taking? Notice that the level, it's actually going to be the smallest level among all the neighbors, because we're going to use a heap pop. So we're going to pop from a min heap. Now after this, we're going to retrieve the row and the columns. And we're going to do that by popping the value. So we're going to use heap pop. And inside this, we have to specify which heap we want to heap pop. So I want to pop from min heap. So now we have the level, we have the row, and we have the column. So what is left for us to do? It's actually to go to see all its neighbors and to add them to the min heap, so that on the next round we're gonna go see the next neighbors. And in the meanwhile, we also have to keep track of the smallest, well, the greatest value we've seen so far on this path. Yeah, so this is currently set to the top left value grid. It will eventually possibly change. And we also have to include a return statement. So what is a return statement? Well, it basically is when we reach the bottom right case, right? So this is going to be set if basically n, or if basically the row is equal to n minus 1, and also the column is equal to n minus 1. Okay, so this is where we just want to return the level that we are at. All right, so if this is true, it must mean that we are on the bottom right case. Okay, so after this, we're gonna go see basically, well, we're gonna go right. We're gonna go see its neighbor to the left. We'll see the neighbor of the current case one cells down, and we're gonna go see the neighbor one cells up. So they're gonna be pretty similar. What I will do is that I will just first, to go right, I need to change the column. So the column has to go, has to increment by 1. So I will just say, well, NC is going to be equal to C plus 1. I don't need to touch the row. We're staying on the same row when we go to the right. And I will basically add this to the min heap if we haven't seen this value yet, or this cell yet. And also if the NC is actually smaller than the value of n, because otherwise we're out of range. So if NC is still in range, okay, and if our current combo at this NC and at this row is not in C, well, first we're gonna add in C this particular combo, so this new column and this row, and lastly we're gonna add this to the min heap. So I will say heap push, and what I will push in it, well, first inside the eap push function, you always have to specify which eap you want to push in, and then you want to basically say what do you want to push. So what we push in is basically three values. First is the level of that the water at this position in the grid. This is found by using the value of the cell of this grid at the new columns and at this new row. And finally, we also want to pass the column. Um, Actually, it's a we're storing the row first, so it's going to be stored like that. And we're also um, passing in the column first. So this is what I want to do to go to the right. We're going to use pretty much the same thing for the left. So for the left, instead of incrementing c by 1, we're going to decrement it by 1. And instead of checking if it is smaller than n, I basically want to ensure that this is still in range in the negative position. So it can be 0. That will work. We are going to use the exact same logic to go down and to go up. So instead of moving the column by 1, we're going to move, well, we're going to increment the row by 1. And this is how we're going to go down, and to go up, we're just going to decrement the row by 1. So this is the exact same logic, right? We're going to just see if that new row is still in the range, and if it is not in scene, if both are true, we're just going to add this in scene and then push that value to the min eap. Notice that the level that we are passing, it has to be the maximum value between the current level and the grid, because this is how we're going to keep track of the greatest value in our path. And that greatest value in our path is basically the threshold, like the t value that we have to render. This is exactly this greatest value in our path, because once let's say the greatest value in our path is 8, and the case that our start at is has a value of 0, well, it will basically take 8 times to have a path that can be used, so I can travel this threshold of 8. Right? So this is how we actually go see the neighbors. So that's pretty much the entire code. We can test it out, and it works. Awesome. In terms of space complexity, so popping and pushing inside a max eap is an operation of log of n, and we have to use a log of n for every single cells. And we know we have a grid of n by n cells, so we're gonna have an n square log n time complexity. In terms of space complexity, in scene we are adding the entire grid, and the grid has a space of n by n again, so n squared. So our space complexity will be n squared. This is definitely the most efficient way we can solve this problem. So I hope you enjoyed this video, and I hope to see you in the next one.